Claremont 3D Design – Benefits of accurate scope definition from layouts. Suppliers and contractors need to see the physical layout in order to provide accurate quotes, as the environment which they have to work in impacts the often missed items for access at height and details of existing systems. P&IDs are not representative of the real world, and most additions to existing plant require more extensive changes than shown on logic diagrams to accommodate new inline equipment. Here are some examples illustrating the issues faced and how this method of work resolves matters. Space required for new equipment, refractometers. The logic of the P&ID makes the work required seem like a simple addition to the existing system. However, the survey identified P&ID errors and found the height to be just over 2.5 meters. The physical space requirements for the new equipment is a minimum height of 3 meters. The physical realities resulted in much more work required than shown on the P&ID. Here's the comparison. The layout on the left shows the work required in red, and this would have been quoted for if just from the P&ID, whereas the layout on the right shows the amount of work actually required, and this reality would not have been identified until after contract agreement, resulting in delays and variation costs to complete the work. Finally, here's the revised P&ID once the physical reality was identified. Old records of existing equipment, reactor replacement. A client requested a project to replace an existing reactor, providing revision 1, which showed 4 flanges on the bottom plate. The option of simply following this instruction could have been taken, but following procedures this was checked against the P&ID, which showed 5 lines on the bottom of the reactor, and that a physical survey confirmed this to be the case. The ISO layout was created to scope the work required to remove each connected spool and piece of equipment. When the client was presented with this information, revision 6 of the GA was discovered, preventing this future error from occurring. Not enough detail of existing equipment, neutralization vessels. Replacement vessels were required on an effluent system. There was only one surviving drawing from 1973, and the quality of the scan was poor. The second vessel was sketched by another party prior to our engagement and did not define locations of flanges. Starting from scratch to correctly define the requirements, the P&ID was consulted, only to find no volume requirements for each stage, making detailed design for fabrication impossible. So a site survey with the client's process engineer identified how the existing system works, and a meeting followed to define the requirements. This resulted in the creation of vessel GAs for fabrication to quote against. Again, if this had not been carried out before engaging the fabrication company, a series of delays with cost increases would have resulted. P&IDs are not to as-built status, leading to scope revisions. Dispex project. For this project, a number of new inline items were required, as well as a replacement of existing with safety upgrades. A site survey revealed many errors, incorrect line sizes, specs and additional items, but the P&IDs had not been updated to show these changes. As previously shown, the ISO layout is able to resolve all issues to correctly identify the full scope of work required, correcting P&IDs before contractors were engaged. Existing bad practices can be corrected or accommodated if surveys of existing systems are carried out. Here's an example of a reducer welded to a flange. This is not good practice, and a minimum of 50 mm is typically required before fitting after a flange. This is how it should be done. An example of this is shown here, where the T requires replacing with a cross as the new upgraded instrument in the same size as the pipe at 40 nominal bore. But since the reducer is welded directly onto the flange, the replacement spool cannot be fabricated in the same manner, so this creates a knock-on effect where more spools must be replaced to create this additional 50 mm. Here it is shown ISO layout format. Evidence of this in the project is shown here, with a preliminary definition from P&ID compared with a well-defined layout from survey, which identified additional requirements of piping route for access, replacement of pipe supports to enable lifting of vessels, replacement of piping to new vessels as existing flanges and old spec, along with additional work to dig out and replace the drainage gully at a lower level, as there is another system which feeds into this. These additional requirements were caught after the contractor had already submitted the cost estimate, but before contract award, so the cost was revised by the contractor, showing an increase from $93,000 to $121,000. These changes would have been identified later, but by that time the delays and additional cost to resolve these would have pushed this cost even higher, as the contractor would have set the wheels in motion for the materials on top of the management of these variations. Here's a full-scale project example. This project required the removal of existing vessels, design and fabrication of a new storage vessel with tanker offloading and export into an existing process, along with smaller dosing system which required the recertification of an existing tank. During Phase 1, surveys were carried out to create CAD ISO layouts of existing systems so that the proposed changes can be added to define the scope of work. The basic layout evolves for more detail, but is not for accurate cost estimates. This shows only what's required for locations of equipment, details of nozzles and access, so companies can supply accurate quotes. The existing fuel oil vessels were redundant, but in order to remove them, the pipe and communication cable still in use on the solvent tank had to be supported by another means, as a walkway had to be removed. This shows a concept design. Once the support was in place, the work could start on the demolition of the fuel oil vessels and pumping system. The concept design shows the work required in red. Here's a series of photos showing the removal of fuel oil vessels and the bases left behind for the new vessel. Once the vessels were removed, work started on the new build from the previously completed design work, which had been upgraded to a 3D model for layout review. The model was also used to complete the bund volume capacity study. Here is a photo sequence of the build starting with a plinth, and the vessel being lifted into place. Scaffold was added to assist the piping install. Then the steelwork was constructed for the new walkway, linking the new vessel to the existing. The design of the new pump system from the vessel was used to assist the construction. The tank farm work was completed when the tank offloading system was installed. The new system had to be routed into existing vessels, requiring platform extension for access. Here's a photo before the works. Once a platform is installed, the new pipe runs and inline equipment in accessible locations and tie-ins to existing. An additional chemical had to be dosed into the makeup vessels, requiring the assessment and recertification of an existing vessel for use with a new pumping system, including transfer from IBCs. This project had multiple changes, but since the basic requirements were unchanged and contingencies added once surveys clarified what was possible, the project was completed within 10% accuracy.